Let's check our understanding about what we've learned about currents so far. So when we connect a parallel plate capacitor with a wire, several things can happen that indicates a current is moving. The wire can get warm as the electrons that are moving through bang against each other and have atomic friction. A thin filament that's in a light bulb could heat up and therefore glow, giving us light, and a compass needle can be deflected. All of these are proof that a current is occurring through a wire. Your book gives a great analogy of water moving through a pipe and the flow of electrons moving through a wire. Now, just as water wouldn't be used up as it spins a turbine going through a pipe, electrons aren't used up just because they are causing a light bulb to light, or deflecting a needle, or running a toaster. That leads us to the law of conservation of current. The current is the same at all points in a current-carrying wire. I may be overemphasizing this, but we need to remember that current is the flow of the positive charge, even though the positive charges don't flow. It's the electrons that flow through a wire. Now keep this in mind as we look at the next diagrams, which will show the positive charges moving. Now current is due to the motion of the charges, and so we can define current as the rate of motion of charges through an electric field. In other words, how many charges pass a given point in a given amount of time. The equation for current is I equals delta Q over delta T, where I stands for the current. Now if the charge Q is measured in coulombs and time is measured in seconds, then current is measured in coulombs per seconds. 1 coulomb per second is equal to 1 ampere, or 1 amp, and here you see the abbreviation for ampere. Another way to look at this equation is to rewrite it in terms of Q. And here we see that Q, the total amount of charge, can be found by multiplying the current times the time interval. The last thing you read on Friday concerned what happens when a current either enters or exits a junction. Now it just makes sense. If water was coming to this top junction, some would go to the top and some would go to the bottom, but it'd still be the same amount of water. For current, the same thing happens. According to Kirchhoff's junction law, the sum of the currents entering a junction is equal to the sum of the currents exiting a junction. Time for another short review. Yay, we're almost near the end. We just need to talk a little bit more about batteries to make sure that you understand them. Now we have seen that if we separate charges on two plates, we have a capacitor, but we need to connect the two plates with a wire and then provide something in between them, some sort of chemicals, so that the charges can be moved from one plate to another and thus replenish the supply. So here we have an electron moving around the wire to the positive plate, and then it travels through the chemicals to return to the negative side. But what exactly is happening in the battery? Here we see that as the charge flows through the wire and reaches the opposite plate, chemical reactions take place within the battery, which cause positive ions to move to the positive plate and leave negative ions to collect on the negative plate, and thus the process continue over and over. Now we know that the electric potential energy is equal to the charge times the electric potential, or voltage, much like the gravitational potential energy was equal to mass times gravity and height. We can now say that the flow of charge in a continuous loop is called a complete circuit, and that is where we are headed to. This separation of charges in our battery, putting the positives up on the positive plate and leaving the negatives on the negative, creates a potential difference. Much like when we raised our animals up to a taller height, gave them a potential gravitational difference. The potential difference established by something such as a battery is called the EMF. EMF stands for the electromotive force. Its symbol is a capital epsilon, and the units for the EMF are volts. So now we see volts, which was our electric potential, has come back again. A battery's rating, whether it's a 1.5 volt battery or a 9 volt battery, is a measure of its electromotive force. Now, when a battery is hooked up to a circuit, due to some of the chemical processes within the battery, the actual voltage is a little bit less than what it's registered at. But for the purposes for this class, we will say that a 1.5 volt battery actually delivers 1.5 volts. And the same thing for a 9 volt battery or any other battery we talk about. So that's it for this video. We've looked at two of the three parts for describing circuits. We've looked at the electric potential or voltage, and we've looked at the current or the amperes. Next we will look at the resistance.